Hello everyone. Today I am going to discuss about derivation of parabolic velocity profile for pipe flow. Hope you will like this video. So these are the contents that I am going to discuss today. Everything starts with the motivation and extensive use of pipes and tubes in our day-to-day life is our source of motivation. So in the morning we need hot and cold water which is transported from their respective storage tanks by these pipes. In the pumps, or you can say in the petrol pumps, we can see these kinds of pipes, and even in our kitchen we can see this kind of gas pipe. In shell and tube heat exchanger there is a large number of tubes present which is used to flow one of the fluid. Now next one is the big pipes you see laid all over the cities in order to transport the drinking water and water for the irrigation. It is used for the slurry transport, but the most important one is the blood vessels that are present inside your bodies in the form of arteries and the veins in which your blood is traveling. So these are also a kind of tubes that are present inside your body. Here we had discussed about Cartesian and cylindrical coordinate system. In the Cartesian system, the point P is represented by x coordinate, y coordinate and the z coordinate respectively, whereas in the cylindrical system we have r system, r coordinate, theta coordinate or phi coordinate you can say, and the z coordinate. So what happens, we have a point P, so first we will make its projection in the xy plane, and the direction from the and the angle from the positive x-axis is defined as theta, so it will give the theta coordinate, whereas z coordinate would be same as in the Cartesian system. So in this way we can make the relation between cylindrical and Cartesian coordinate systems. Before starting from the assumptions, we will discuss a bit about the system. So we are provided with a pipe in which fluid is flowing in the horizontal direction. So consider the direction of fluid flow would be Z, and another direction, that is radial direction, should be R in the cylindrical coordinates. So it is in such a way that pressure P0 is applied at Z equal to 0 and PL is at Z equal to L, such that P0 is greater than PL. So due to the pressure gradient there is a movement of fluid from Z equal to 0 toward Z equal to L. Also, we had enlarged a small portion of a pipe in the figure 4, and we had shown all the three components of the velocity. So this one is the VR component of the velocity, this one is the V theta component of the velocity, and this one is the VZ component of the velocity. So the pipe is having radius of capital R, that is the distance from the center of the pipe to the wall of the between center and wall of the pipes. Now next one is the assumptions. So the first assumption is that the flow is steady in nature. So what does it mean? There is no variation of any property with respect to time during the flow. So we can write that dou t of any quantity equal to 0. So also the quantity may be velocity or you can say density. So that's why dou t of v is equal to 0. Next assumption is that flow is fully developed. So what does it means? That since our fluid is flowing in positive z direction, so dou z of Vz equal to 0. So no variation of velocity component Vz in the z direction. Next assumption is that we have considered the axis symmetric flow. So what does it mean? That there is no variation of vz component of velocity in the theta direction, and also v theta equal to 0. If there is a presence of v theta, so the condition axis symmetric is violated, so that's why v theta is also equal to 0. Also we can also show the Cartesian coordinate system in the figure 4. So x direction is in this way, whereas our z direction as same as in the cylindrical coordinate system, whereas our y direction is upside, and so that's why our gravity is acting in minus y direction. The next important assumption is laminar flow. The flow should be laminar. It means that it is the smooth flow in which the layers are moving parallel to each other in a highly ordered motion, so that these are not making any disturbance in the movement of another corresponding layer, and these are moving parallel to each other. For that we are defining Reynolds number, which is a dimensionless number, to check whether the flow is laminar or not. So Reynolds number for pipe is given as rho v average d divided by mu, where rho V average and mu are density and average velocity, viscosity of the fluid respectively, and small d is the diameter of the pipe. So if this Reynolds number is less than 2100, so flow is laminar. Next assumption is incompressible flow. So it means density remains constant. So dou t of rho equal to 0, or dou t of any spatial coordinate equal to 0, because density does not change with time or spatial coordinate, because it is incompressible flow. Next one is the end effects. So end effects are related to the entrance length. So what entrance length is? It is a length needed to build up the fully developed flow inside the pipe or any geometry. So it is defined as the entrance length as shown in the figure 6. This region is known as the entrance region, and next region is the fully developed region. So we are considering only fully developed region. So end effects are neglected, and this entrance length is given by 0.035d multiplied by Re, which is Reynolds number. This relation is taken from BSL book. And next assumption is fluid should be Newtonian. After considering all the assumption, now we will solve the continuity equation, or you can say mass balance equation, in order to simplify our problem. So it is the continuity or mass balance equation for cylindrical coordinates taken from BSL textbook. Now our next task is to solve this equation, or you can say simplify this equation one by one and see the contribution of each term. So the first term, dou t of rho equal to 0, because the density is constant due to incompressible flow, and also it can be 0 due to steady state assumption. Since we have no information of VR till now, so this term remains as it is. Next term, since v theta is 0 due to axial symmetry, so it is also equal to 0, and next term is also equal to 0 because rho is constant, so it can be taken outside, whereas dou z of vz equal to 0 due to fully developed flow. So in left hand side we had left with only one term, which is 1 upon r multiplied by dou r of rho r vr, which is equal to 0. Now our aim is to solve this equation. Since rho is constant, so we had taken this rho outside, and we get rho up, divided by r, dou r of rvr equal to 0. So when rho divided by r taken to other side, finally we get dou r of r vr equal to 0. Now we have to solve this equation. So we will integrate this equation with respect to r, and we get r vr v small r, it means equal to any constant. Let this constant be given name of a. Finally we get v subscript small r equal to a divided, which is constant, divided by r. So now we will solve the boundary condition in order to simplify the situation for the radial component of the velocity. Since we all know at the boundary the layer of fluid corresponding to the boundary having velocity 0 because of no slip condition at boundary, the velocity of a fluid layer corresponding to the rest solid layer at the boundary is equal to 0. So we got V capital R means that is velocity at R equal to capital R at the boundary of the pipe equal to 0. So we get A upon capital R equal to 0. So finally the value of constant A is equal to 0. So from this we can take it that the value of radial component of velocity A v subscript small r is also equal to 0. After solving the continuity equation, now we will discuss about the momentum balance, or we can solve the momentum balance equation for r, theta and z direction respectively. For this we are using a table 1 which is taken from the Burr, Stewart and Lightfoot Transport Phenomena book. So it contains information about equation of motion for a Newtonian fluid with constant density and viscosity for the cylindrical coordinate system. So first we will these are the several results that we got from the different assumptions. Now with the help of these results from assumptions and continuity equation, we will solve the equation. Now first we will discuss about our momentum, our directions momentum. So this term equal to 0 due to steady state, this term is also equal to 0 due to Vr equal to 0, this term is also equal to 0 due to the presence of V theta and Vr, both are equal to 0. This term is also equal to 0 due to the presence of Vr, and this term is also equal to 0 due to the presence of V theta, which is equal to 0 due to axis symmetric. So our whole left hand side will be equal to 0. This on the right hand side, this term exists. This term is also equal to 0 because we are equal to 0. This term is also equal to 0 due to V are equal to 0, and it is also equal to 0, V are equal to 0. This is also equal to 0, dou theta of V theta equal to 0, or simply V theta is equal to 0 due to axis symmetric. Now only these terms, two terms exist, so we can write our momentum equation as 0 equal to minus dou r of P plus rho g r, where g r is a gravity in r direction. Now we will discuss about theta momentum equation. So first term equal to 0 because steady state assumption, or also V theta equal to 0. This term is also equal to 0 because we are equal to 0. This term equal to 0, V theta equal to 0 due to axis symmetric. This term is also equal to 0 because dou z of V theta equal to 0, and this term is also equal to 0. Vr and V theta both are equal to 0. This term exists. Again, this term equal to 0 because V theta equal to 0. This term is also 0. This term is also 0 because V theta is 0. This term is also 0. Vr equal to 0. So we had only left with two terms. So our theta momentum equation becomes this one, 0 equal to minus 1 upon r multiplied by dou theta of P plus rho g theta, whereas g theta is gravity in the theta direction. Now we will solve for the jet momentum balance equation. So this term due to the steady state equal to 0, this term due to the presence of VR equal to 0, this term due to the presence of state V theta and also due to the axis symmetric condition equal to 0, and this term is equal to 0. Why? Because dou z of Vz equal to 0 due to fully dual flow condition. So we are left with, on the left hand side all the terms are equal to 0. Now we will come to the right hand side. So this term exists, this term also exists, this term is equal to 0 due to axis symmetric condition, and this term is also equal to 0 due to fully dual flow. Since there is no gravity in this z direction, so the this term is also this term is also equal to 0. So finally we get equation of momentum in z direction as 0 equal to minus dou z of p plus mu whole multiplied by 1 upon r multiplied by dou r of r multiplied by dou r of Vz. So these are the required equation of momentum in r, theta and z direction. Now we had obtained momentum equation for r, theta and z directions. Now we will solve it one by one for r and theta direction. In the figure, both cylindrical and Cartesian coordinates are shown. So from the figure we can easily obtain that the direction of gravity is aligned in negative y direction. And in figure 7, we had provided the unit vectors in the rectangular and cylindrical coordinate system. This is taken from the BSL, and based on this figure, the relations had been developed between unit vector in Cartesian system, which are x, y, and z, and their corresponding unit vectors in the cylindrical coordinate system, which are theta, r, and z. So these are the relation between these two kinds of these two kinds of the systems. One is Cartesian, next one, another one is the cylindrical. So since our gravity is present in minus y direction, so we have to use this del y component of the Cartesian system, and we have to find out its corresponding cylindrical coordinate system. So the value of g become minus g sine theta, which is a component in r direction, that is gr, and multiplied by del r unit vector in r direction minus g cos theta, which is a component g theta present in theta direction, multiplied by del theta, which is a unit vector in theta direction. Now we will solve for r momentum equation, and in place of gr we will substitute minus g sine theta, and when we integrate this equation with respect to r, we came to know that pressure equal to minus rho g r sine theta plus a, which is constant, is a function of theta and z, because we are integrating with respect to r. In the similar manner, we will solve for the theta momentum. So for theta momentum, we know that value of g theta is equal to minus g cos theta. So this g cos theta is substituted in place of g subscript theta, and when we integrate this equation with respect to theta, and we know that integral of cos theta d theta equal to sine theta, so finally the pressure is equal to minus rho g r sine theta plus p, which is a constant, is a function of r and z. Why function of r and z? Because we are integrating with respect to theta. The Cartesian coordinate system are shown x, y, z in this figure, and this is the projection of the point P in this system, where R is the distance from the origin to the projection of this point, and theta is the direction from the positive x-axis. So the y coordinate can be represented as y equal to r sine theta. Now we will substitute the value of r sine theta, which is equal to y. So we get the pressure P equal to minus rho gy, which is showing the hydrostatic variation with respect to y, plus C. Now this C is a constant and is a function of z only. Up to this time we had solved the momentum balance equation for r and theta direction. Now our aim is to solve the momentum equation in the z direction. The simplified momentum equation in the z direction appears like this. So by clearly observing, we can see that the first term, that is minus dou z of p, is completely a function of z alone, while the next term is completely a function of r alone. So this condition can only be satisfied when these terms separately will be equal to a constant. So from this we get that dou z of p, or mu multiplied by 1 divided by r, dou r of r, dou r of vz, equal to a constant c. So both these terms are equal to a constant c. So now we will solve these terms one by one in order to get the value of the c and simplified the equation. So based on the analysis, we get that minus dou z of p equal to c. So by integrating this equation with respect to z, we get p equal to minus cz plus d, where c and d are constant. So based on the boundary condition, now we have to find the value of c and d respectively. So we all know that pressure at z equal to 0 equal to P naught, and pressure at z equal to L at the end of the pipe, another end of the pipe, is equal to capital P subscript capital L. So these are the boundary condition. Now first we solve for z equal to capital L. So value of pressure at z equal to capital L, we have to in place of z we have to write capital L. So we get capital PL equal to minus C capital L plus D, and pressure at Z equal to 0. So this term CZ term equal to 0 because Z equal to 0 here. So finally we get capital P not equal to D. And when we substitute this equation here in this equation, we got the value of C. So the pressure difference applied across the pipe is capital P naught minus capital PL. So finally the value of C is coming around capital P naught minus capital PL whole divided by L. So we can write it as delta P divided by L. So we can substitute this value of C and D in the equation A. So finally we get the value of pressure at any point Z is equal to small p is equal to minus capital P naught minus capital PL whole divided by L multiplied by Z location, that is the location, plus capital P naught, that is the pressure at Z equal to 0. So differentiate the expression with expression of small p with respect to Z. So we get that it is equal to minus delta P divided by L. So finally we can write that dou Z of small p is equal to minus delta capital P divided by L. So which is also equal to C, which is our constant that is desired to be found. Up to so far we had got the value of C, which is equal to minus delta P divided by L, which is also equal to mu multiplied by 1 divided by R multiplied by dou R of Vz. So by making a small rearrangement in the terms, that is taking the L with the mu and R with the delta P, we get that dou dou R of Vz is equal to minus delta PR divided by L into mu, where mu is a viscosity. So integrating this equation with respect to R, we get R dou R of Vz is equal to minus delta P multiplied by R square whole divided by 2L mu. 2 comes from the integration R square upon 2, plus we get the constant of integration, which is considered to be C1. Now dividing both sides left and right with R, so we get dou R of Vz equal to minus delta P R divided by 2L mu plus C1 divided by R. Now again integrating this equation with respect to R, we get Vz, which is the velocity in the z direction, is equal to minus delta P multiplied by R square whole divided by 4L mu plus C1. The integral of 1 upon R is equal to ln R plus C2. So here C1 and C2 are constant. So our next main aim is to find this, what is the value of this C1 and this C2. So for this we have the two boundary conditions given. So remember, the first boundary condition is that at R equal to 0 means here at the center the tau Rz, which is the shear stress at the center, must be finite. Means value should be finite. It cannot be infinite at the center. And the second boundary condition is that at R equal to capital R means at the boundary of the pipe Vz equal to 0, that velocity at the radius, or you can say at the R equal to capital R, or you can say at the boundary of the pipe, is equal to 0. This is because due to no slip condition. So velocity at the R equal to capital R, or you can say at the solid boundary or the pipe boundary, is equal to 0. So these are the two boundary condition based on which we can calculate these constants C1 and C2. Now our main task is to find the value of C1. So we will use the value of Vz, or you can say expression for the Vz, which is this one. So it has a term of C1 into natural logarithmic of R, which is a critical term from which we will came to know the value of C1. So we know that tau Rz is finite, so it means Vz also be finite at R equal to 0. So we can divide the Vz into two components. First component is minus delta P R square divided by 4L mu, and the second component is C1 logarithmic of R. So this component is finite when R tending to 0, but what is the value of C1 ln R at R tending to 0? For this we have plotted a graph on the MATLAB between natural logarithmic of R and R. So as R tending to 0, as observed in the graph, R tending to 0, the value of natural logarithmic of R is tending to infinity, minus infinity. So the value of C1 must be equal to 0, otherwise velocity is not z component of velocity is not finite at r tending to 0. So from this observation we came to know that C1 must be equal to 0, and finally for Vz we got the expression Vz equal to minus delta p r square divided by 4L mu plus C2, which is a constant. Now we have to determine the value of C2. Now we have to find the value for C2, so it is the expression for the Vz, and let this equation be given number 1. So we know that there exists a no slip boundary condition. So what does it mean? The speed of the fluid layer in direct contact with the boundary is identical to the velocity of this boundary. So we know that velocity of boundary is equal to 0. So the velocity of the fluid layer which is in direct contact with this boundary is also equal to 0, and we also know the value of radial coordinate small r is equal to 0 at the center, whereas the value of this radial coordinate at r is capital R, which is equal to radius of the pipe at boundary. So we get that Vz at small r is equal to capital R, or velocity of z component at boundary is equal to 0. Now when we substitute the value of Vz and small r in the equation 1, so we can find out the value of C2, and when we substitute this value in the expression of Vz, we finally got Vz equal to delta P r square minus a small r square whole divided by 4L mu. And now when we multiply or divide both sides with capital R square, or you can say that when we take R square common from this equation, so we came to know that Vz can be divided into two factors. First is delta P R square divided by 4L mu, multiply by bracket starts another factor 1 minus small r square divided by capital R square, and bracket closes, it is the next factor. So these are the two factors which are representing the Vz, and based on the Vz we can also find out tau Rz. We all know that tau Rz equal to minus mu dou r of Vz. The another component is 0 because Vr component is equal to 0. So when we substitute the value of dou r of Vz in the expression of tau Rz, we finally came to know that the value of tau Rz equal to delta P r whole divided by 2L, and from this we can nearly observe that Vz is proportional to the r square. So it is the quadratic relationship between Vz and the r square, that is the radial distance from the center of the pipe, or you can say that it shows the Vz shows the parabolic profile as observed in the figure 10, that the parabolic relationship is followed between radius and the velocity in the pipe flow, and whereas the linear relationship exists between tau Rz and tau r, which is represented by this line. So tau r z equal to 0 at the center, whereas it is maximum at the walls, and it follows the linear relationship with r, whereas velocity follows the parabolic relationship with the radial distance from the pipe. Now we have to find the average velocity of the fluid, which is defined as the ratio of total volumetric flow rate divided by the cross-sectional area. So it is the expression for the z component of velocity. So Vz average can be defined as the volumetric flow rate divided by the cross-sectional area. So it is defined as integral 0 to 2 mu. It is theta integral 0 to r integral. It is r integral vz r dr d theta whole divided by cross-sectional area, which is equal to 0 to 2 pi integral of theta 0 to 2 pi 0 to r integral of r dr d theta. Now we will substitute the value of vz here from this expression, and we will now try to solve the expression in numerator and denominator. Since we know theta is independent of r, so we can take the theta integral first and then dr integral, so we can interchange the order of the integrals, so like this. And the integral in the denominator is directly equal to area of the circle, which is equal to pi r square. And finally we know came to know that vz average equal to this factor delta p r square for l mu we can take outside, and 2 pi is the integral come from the d theta integral. So finally we have to solve this integral. So this integral can be solved as follow. The r raised to power 1 here and a small r raised to power 3 divided by capital R square. Since capital R square is constant, so it remains as it is. So the integral is capital R square divided by 2 minus capital R square divided by 4r square minus, when we substitute the value of the limits, it is the upper limit with, and it is the lower limit which is 0 and 0. So the value of this r square is cut, and here the power of r square will changes into r square, and finally it is the integrals value will be equal to r square divided by 4. And when we substitute this value in place of this integral, we came to know that vz average equal to 2 pi multiplied by delta p r square divided by 4 l mu multiplied by r square divided by 4 whole divided by pi r square. So we can cut this r square from this r square, this 2 from 4 it becomes 2, and this pi from this pi, and finally we got the expression that vz average velocity of the fluid inside the pipe is equal to delta p r square divided by 8l, which is the length of the pipe, and mu, which is the viscosity of the pipe. So it is the required expression for the average velocity of fluid inside the pipe. Now we have to find out the maximum velocity. So it is the expression for the velocity of a fluid in the pipe. So Vz will be maximum when this term would be maximum, and its maximum value from the observation can be found out equal to 1, and it exists at r equal to 0, and we all know that r equal to 0 is the center of the pipe. So the maximum velocity will exist at the center of pipe, and it is equal to del p r square divided by 4l mu. It is the value of the average velocity, and it is the value of the maximum velocity. So ratio of the average velocity and maximum velocity is come about 1 upon 2. So we can say that the maximum velocity is twice to the average velocity. Same thing shown that the Vz in the figure, that Vmax exists at the center, which is r at r, or you can say at r equal to 0. Based on our learning so far, we will now try to solve a problem. Suppose we have provided a fluid which is passed through a pipe in such a way that the first particle can be seen after 5 minutes on the another end of the pipe. Suppose it is the one end of the pipe. Let this end be given name 1, or you can say z equal to 0, and this is another end given name 2, or it is at z equal to L. So after 5 minutes, the particles take 5 minutes to reach on the another end. There are a large number of particles present in the fluid, but the first particles is observed on the another side after 5 minutes. So based on this, what should be the average time spent by the particles, different particles inside the pipe? And flow should be considered to be laminar, and such that Reynolds number is less than 2100, and the property like viscosity and density is assumed to be constant. Now you can pause down the video and think about the solution. From the problem we came to know three important facts. First, particles which arrive at the another end means it is the fastest particle, so it should have the maximum velocity, and we know the relationship for a pipe flow between maximum velocity and average velocity. So we will use these 3 points in order to solve the problem. Now first thing is that whatever will be the velocity of the particles, it has to travel the same distance, that is L, toward the end of the pipe, and we know velocity is given by distance upon time. So for the maximum velocity the time should be minimum, whereas for the average velocity we have average time, and our main aim is to calculate this average time spent by the particles inside the pipe. So we will divide Vz max by Vz average, and it will give us that Vz max upon Vz average equal to T average divided by T minimum. So T minimum is the minimum time spent by a particle inside the pipe. We know that Vz max upon Vz average equal to 2. So we will came to know that T average, that is the minimum time spent by the particles, or you can say that fluid particles inside the pipe, would be 5 multiplied by 2, which is equal to 10 minutes. Now we have to calculate the average volumetric flow rate. We know average volumetric flow rate equal to average velocity times the cross-sectional area. After substituting the proper value of V average and the cross-sectional area, our volumetric flow rate is coming to be delta P divided by L times pi d raised to power 4 divided by 128 mu, where d is the diameter of the pipe. Now we can also represent it in forms of Vz average multiplied by the cross-sectional area equal to the same expression. So we can represent delta P equal to 32 mu V average L divided by d square. Now we will divide both the sides of this equation with rho g, and we came to the equation, that is delta P upon rho g equal to 32 mu V average L whole divided by rho g d square, where delta P upon rho g is the loss of pressure head, and this equation is commonly known by the name of Hazen-Poiseuille equation. Now, based on this concept, we will try to solve one question. Suppose we have been provided with the two pipes. One pipe is having dia of 20 centimeter, whereas another pipe maintaining the same flow rate in both the cases. The larger pipe is having dia 3 times the smaller one. Now we have to estimate the ratio of average and maximum velocities in both the cases, and also the pressure drop per unit length in both the cases, or we can say that we have to find the ratio of pressure drops in both the cases. The factors like viscosity and density are kept to be constant, so you can pause the video for some time and think about the possible answers. It is the expression of the V average, and by substituting values we get Q1 equal to Q2 given in the problem. So we came to know that average velocity in case of smaller dia pipe would be 9 times to the average velocity in the larger dia pipe. Same would be case of the maximum velocity, that maximum velocity in the smaller dia pipe would be 9 times to that of larger dia pipe. This is because the ratio of average velocity and maximum velocity will remain same, and since Q is constant, we substitute the values of different parameter in this equation, and finally we came to know that only varying factor are pressure drop per unit length and diameter. So finally the ratio of pressure drop per unit length in case 1 to in case 2 is equal to 81. So these are the list of the references. Last but not the least, I just want to say thank you to one and all for listening patiently. Thank you once again.